So any doubts from yesterday that you want to ask me? Was there anything that was not clear? Feel free to put it in the chat box and I can try to answer any questions that you may have had. I hope you were able to try that exercise which I gave. Anybody tried it? No one? Any doubts? Anything from yesterday? So what did we do yesterday? We basically introduced MATLAB or Octave, right? And we showed that it is very useful in a number of courses that you do in engineering, starting from the very first year actually, right? So I keep recommending to teachers that when possible they should allow the students to do some of the experiments in Octave. The advantage is it's easy, free to all the students, public domain, and very easy to learn, right? It's not that difficult, right? Yesterday, I have not told you about for loops, which are also very easy, nothing great about it. So let us give a simple example for loops today. So you need for loops sometimes. I have already told you that the for loop is sort of inherent in MATLAB. So if you remember, we said if x equal to, let us say, start from 0, right? And in steps of pi by, let us say, 10, keep going till pi. Okay. Then if you say sine of x, right, then it applies the sine operator to each and every element. So the for loop is not required to do something like this. See, we don't have to say something like, or I equals 1 to, let us say, 11, right? Sine of x of I. We don't have to say this. Okay. But this is how for loops are written. So for loop means you have to write like this, for, right? And you can choose some variable like I, j, k, whatever. I suggest you don't use I, j, k, because as I told you, I stands for that complex number imaginary part I. So better not use I, j, k. Let us say we use something else like, let us say, t, right? Or t equals 1 to 10 or whatever. This can be either 1 colon 10, or it could be some linear space, 0, 1, whatever you want. Something that gives me a vector. Okay. Also say for t equal to 1, 2, 3. Right? And then you can write any statement here, such as, let us say, display t, and then write end for. It will accept both end and end for. Okay. So if I try to execute this, right, you will see that it will display t for each of these values. That's clear. So for loop syntax is choose some loop variable and equate it to some vector. Okay, it could be 1, 2, 3. It could be 1 to, let us say, 10. Right? And you can write down any number of statements in between. Okay. It doesn't have to be a single statement. So suppose our interest is in calculating, some of you may remember this formula. Anybody remembers the formula 1 square plus 2 square, etc. 1 square plus 2 square plus 3 square. The sum of all the squares. Does anybody remember? You would have done it as part of your 10th standard, or right? Anybody remembers? Yeah, I think Gunavardhan has given the correct answer. N into n plus 1 into n plus 1. That's correct. So just out of curiosity, suppose I take n equal to, let us say, 10, and I say for t equal to 1 to 10, right? Suppose I calculate t square. Okay, to do t square, I have to do t square. And let us say I sum it to some total. Okay. And here I may have initialized total to 0. Okay. And then I will put end for here, or end whichever you want. And then I'll say display total. Okay. So this is an example to calculate the sum of squares. Okay. So the sum of squares happens to be 385. Okay. So this is another example of for loops. But frankly, you didn't have to do this. Okay. You just have to take 1 to 10 as it is, right? And then, square each element by putting this and then put sum. Okay. So this is good enough. You really didn't have to write a for loop. Okay. So please know that for loops, try as far as possible to avoid for loops, etc. Right? It's not really required, right? But just in case, sometimes you are having some difficulty and you feel it is more easy to write a for loop, then it's okay. But often, something like this will be sufficient. Is this clear to everyone? While loops are similar. Okay, let us try writing a while loop. While loop is also very similar. Okay. So suppose I want to write a while loop for the same application. Let us say t is initialized to 1. Okay. And I can say while t is less than or equal to 10. Right? And then total equal to 0. Right? Then I'll write total equals total plus t square. And t equals t plus 1. So if you do this, it will keep incrementing t and ultimately t will become 11 and it will stop. And now we can display your. Let me put semicolon here to avoid all those calculations being shown. Okay. So if I do this, I will it's the same answer 385, right? And while loop is very similar, while and some condition. So in this case, the condition was t less than or equal to 10 or something like that. Okay. So just a minute. Yeah. Any doubts in the while loop? Okay, let me just, I forgot to mail the other thing to you. So I sent you the file while loop. Okay. You can also write functions. Okay. See, for example, just now, I think Guna Ranjan, what is his name? Gunavardhan. He has sent a function for sum of all the squares, right? So suppose we wish to write that. So function, right? Let us say sum of squares. Okay. And it takes as input n. And here I want to return it to some value. So I can say result equal. So your function has to return some value. So you can say result equal to, and then here you can say result equal to n times n plus 1 times 2n plus 1 divided by. Then later you can call this function and write display sum of squares. Okay. Okay. So semicolon here. So if I run this, okay, I'll get the same answer. Okay. So, the way to write a function is think of a name and then write all the parameters that it is supposed to take. There can be more than one parameter, n, comma, m, etc., etc., etc. And then you need to return some value. You can return more than one value. Okay. Um, so let me send this also to you. Chat box. Come on. Okay. So let us write one more function. Let us say we want to return uh, the area of a triangle, right? And maybe the perimeter of a triangle. So let us say I will call this function area and perimeter. So what will it take? It will take the three sides, side A, side B, side C. And it will return two things. One is area, the other is perimeter. So how do I write this function? I believe, maybe first we have to check whether it is really a triangle or not. Okay. So how do I check? The sum of the two sides of a triangle must be greater than the third side. If that is not true, we can, say that it is not a triangle. Okay. So if A plus B is less than or equal to C, or B plus C is less than or equal to A, or C plus A is less than or equal to B. If one of these conditions is true, that means it is not a triangle. So maybe we can display not a triangle. So this is an example of how to use the if loop. Okay. And you can set area perimeter. You can say area equal to maybe 0, and the perimeter is also equal to 0. Okay. So if followed by a condition and any number of statements, then followed by end. Assume that everything is fine, there is no problem, it's a triangle. Then we calculate that semi-perimeter, which is A plus B plus C divided by 2. Then the area is nothing but S times S minus A times S minus B times S minus C. I think multiplied by half, I think, right? And I think multiplied by square root of this. I forgot the formula now. I hope this is the correct answer. So square root of S times S, there is no half, I think. Correct me if I'm wrong, I'm making some error. So S times square root of S into S minus A into S minus B into S minus C. And then perimeter is very simple, A plus B plus. Okay. So if I run this, I would have defined the function. Okay. So first let me try this area peri. Let me give something which is not a triangle, 10, 5, and let us say 19. So this is not a triangle. Okay. Oh, there is some. Why is it giving this? Okay. After saying this, it should see here. It should not be end if. It should be else here. Only if it is not a. If it is a true triangle, it should come and do all this. Otherwise, it is coming here and trying to do it even here. So my apologies. So there was a bug in this program. Okay, now let us try area perimeter. Let us say 10, 5, and 19. Okay. So here it's not, whereas if I try a 3, 4, 5, this is a right angle triangle. Okay. So the area is 6. So if you want both the area and perimeter, I can say AP equal to. Okay. So the perimeter is 3 plus 4, 5, 7 plus 5, 12. And the area is half times 3 times 4, which is 6. Okay. So we can try another example, which is 7. 6. Okay. So let me give this also to you as a example. Okay. Any questions? Any questions in how to define a function? So we quickly reviewed how to write functions, while loops, for loops, if then else statements. Okay. So anybody who knows basic programming, it's all the same, right? The R is very similar to C language. Okay. The same and will be there, two ampersands. Okay. So you guys possibly know all this. Okay. So let us write slightly more, maybe I'll give you one more example. Let us try to do something more ambitious, right? I don't, how many of you have done a course on digital logic? Has anybody not done a course on digital logic before? Digital logic? Anybody who has not done? So can I assume that everybody has done digital logic design? All right. So in that case, I will show you this thing called as linear feedback shift register. So you can find it on Wikipedia. Okay. So this is a useful circuit, right? It looks like this. Okay. So this one shows a linear feedback shift register with 16 flip-flops. So it is nothing but a shift register. Okay. It's nothing but a shift register. Okay. So let me make it up here. Okay. So suppose I have 3 flip-flops. Assume that they're all Dave type flip-flops. So what I could do is I could connect them as a shift register. The clocks are all connected, so don't worry about the clocks. I don't want to show all that. Right? Now suppose I take these 2 points and take their XOR. XOR is considered as a sum. You may know that XOR of 2 bits gives me the sum, not the carry, just the sum, right? So for example, if I have 0 plus 0 the answer is 0. That's why XOR will also give a 0. If I try to add 0 and 1, the answer is 1. So XOR will give a 1. 1 and 0, the answer is 1. And if I give 1, 1, the answer is again 0, which is just the sum, not the carry. So the XOR is what is called as a sum. So I have in a way summed up these two bits and I am feeding it back to this. Okay. So this is known as a linear feedback shift register. It's a 3-bit LFSR. It's a 3-bit LFSR. Now, where is it useful? Let us try initializing the LFSR to, let us say, 001. Okay. So suppose I put 001. Now, can anybody tell me what will happen if I clock this? What will be the new state? What will be the new state? Can anybody tell me? See, this 0 and 1 are being given to the XOR gate. So the output of the XOR gate will be 1. And that is getting shifted into this flip-flop. And these 2 bits will get shifted in here. So it went into a new state, which is 100. What will be the next state? Akanksha. What is the next state? Manish. You can type in the chat box. You don't have to unmute and all that. What will happen? What state will it go to? I have 100 in the 3 flip-flops. So there is a 0 sitting here in the second flip-flop and the 0 sitting here. So the XOR of the 2 will be 0. So that will get shifted in here. And this 1 and 0 will get shifted because it's a shift register. In the next state, it will be 1, this 1 and this 0 will get XORed. And that will come here. And the 0 and 1 will get shifted in here. Okay. So this is just a shift register. The 0 and 1 will give me a 1 and then 1 0. Then this 1 and this 0 will get XORed and I'll get 1 1. Then this 1 1 will get XORed and I'll get a 0 1 1. Then finally this 1 1 will get XORed 0 0. So we seem to have gone back to the initial state. Okay. So we started with 0 0 1. Now it will again go through the same cycle, isn't it? So if you refer to 0 0 1 as 1, right? 0 1 0 is 2, 1 0 1 is 5, 1 1 0 is 6, 1 1 1 is 7, 0 1 1 is 3. Okay. And then we went back to 1. So you see it's producing sort of pseudo random numbers. So there is no sequence. It sort of randomly goes from 1 to 4 to 2 to 5 to 6 and 7, 3. So it appears like a random or a pseudo random sequence. I call it pseudo random because if I give you the seed of this, okay, this is not like a seed, okay, then I can predict the sequence. But if I don't tell you the seed, then the next number is hard to predict. Okay. So this is useful in generation of random numbers or random data. And if you see the Wikipedia page, they tell you, the they have given a lot of these examples for a 3-bit LFSR, 4-bit, 5-bit, 6-bit, etc., etc. Okay. So this flip-flop See, why did I connect it like this? Why do I have to connect it this way? Is it that I should only take the feedback of last two bits? Would it do any difference if I take let us say I could have also done something slightly different, right? I could have possibly, I could have taken, let us say, four flip-flops. Okay. What prevents me from taking this input and then this one and maybe this one and then take the XOR of these three and then fill in it. So I can create a number of such topologies, and I'm be curious to know what that will do. Okay. So there is a way to describe this topology, right? We write 1 here, x square here, x cube here, and x power 4 here. It is just a notation, okay? It doesn't mean anything. So you may, if you are thinking, what does it mean? It doesn't mean anything. It is just a notation, okay? Then notice that I am summing x power 4 and then x and x square. So I can write this compactly like this. Sometimes they also show this one. Okay. This is not strictly necessary, right? But people are doing it, so let us leave it like that. So x square x power 4 means the output of the first flip-flop, the output of the second flip-flop, right, and the output of the last flip-flop. These three are being XORed. Okay. So that is what is being shown here. Is that clear to everybody? So this is 1 plus x cube plus x power 4. So let's try this one. Let us take a 7 bit, okay, 6 bit x power 5, x power 6. So let us try writing the shift register for that one. I want you to try helping me when I'm doing this. So I'll have 6 flip-flops or 7 flip-flops, depending on whether I want to. Let us say 6. So as I told you, this means 1, x square, x cube, x power 4, x power 5, and x power 6. And in this case, they are saying x power 5 and x power 6 are being taken and being connected to 1. So this means 1 plus x power 5 plus x power 6. So the question now is, so if I give you this polynomial, right, how do I predict the sequence? Okay, if I want to simulate this LFSR. Okay, so in this example, if I know how to write this, and if I tell you, hey, the seed is 0, 1, 1, 1, 0, 1, can you tell me what is the next number? You will simulate it. You will say 0 and 1 XOR, that will become 1. Then everything will shift. So you will come back with this answer for me. I want the program to do it for me. Okay. I want the program to do this for me and tell me whether it can do that. Okay. Is everybody clear on what the problem is? What is the problem we are trying to solve? Everybody is following me, or is it going too high? Are you following? Ashwin, Nipunya, following? Akanksha says yes, sir. Very good. Nishchal. Okay. Now here is another thing here. These guys have given a simple compact way of describing this tap. Okay. What he means by tap is, right? In a 4-bit LFSR, the last two bits are being tapped and these two are not being tapped. So 1100 means that the last two bits are being tapped. Okay. Here again the last 5 and 3 are being tapped. 4 is not being tapped. So 5 is being tapped, 4 is not being tapped, 3 is being tapped. 6 and 5. Okay. 7 and 6. This is 8, 6, 5, 4. So 8 and 7 is not being tapped. So 6, 5 and 4. 9 and 5. So 9 and then 5. Now you may be curious, hey, why are they coming up with these LFSRs? What is so great about these polynomials? The polynomials which are shown here, they are going to generate the longest sequence of random numbers. Okay. Otherwise, if you take this example here, right? See here, I started with 1 and then 4, 2, 5, 6, 7, 3. See, that is the longest possible. Because with 3 bits, there can be 8 numbers, right? So here 1, 2, 3, 4, 5, 6, 7 numbers are there. The only number which is missing is all zeros. Okay, and I can't put all zeros because if I put all zeros, it will keep cycling there itself. It will get stuck there. So for a 3-bit LFSR, 7 is the biggest sequence. Okay, so number of states 7 is the largest I can get. Okay, so it's called as a maximal length. So this is a maximal length LFSR. Now, not all polynomials will give you maximal length. Okay. So if I take this example here for 9 bits, okay. So how did they figure out that 9, 5 will give me the maximum length? It will give you 2 to the power 9 minus 1 states. Okay. They must have done simulations, etc. to figure this out. So if you take something else, if you, for example, took 9, 8 and XORed and put it back, it may not give me all the 511 states. Okay. So the problem given to you is the input will be a polynomial, and the polynomial can be given to you like this, either a bit sequence like this or a compact hexadecimal number like this. What is this hexadecimal number? It is this only. Okay. This number, the binary number has been written as hexadecimal. So for example, 11 is 3, 110 is 6, 1100 is C, 10100 is 14. Okay. So like that, somebody has come up with the hexadecimal equivalent. So this is a compact and nice representation. So we can write a function, right, which takes the the LFSR, the polynomial in this compact representation, right, and the current state, okay, and gives me the next state. Okay. So LFSR next state. It takes as input, let us say, the number of flip-flops. Okay. And then current state, right? And then maybe the polynomial. So this is the function I want to write. So this is a little bit more ambitious program. Now, how will the I need to somehow extract this 11100 sequence. So I have got B8 and I want to extract this. So how do I do that? Okay. So first of all, remember that you are allowed to write 0xc, etc. Okay. So it recognizes hexadecimal numbers. Okay. You can get bit get. Okay. So if you say bit get 0xc, let us say 1, and then 2, then 3, then 4. So it will give you 1100. So like this. Okay, this is 1100. Okay. Similarly, I can do bit get of, let us say, 0x110. And how many bits are there? There are 9 bits. So I can write 1:9 here. Okay. So this will give me the sequence. I may want 9 to 1. So 9. Okay. So this is what I want. 100010. So 10001 followed by 4. So 3 zeros in between and 4 zeros outwards. Is that clear to everybody? Okay. So what did I do here? I applied the bitget function, which extracts the bits of this hexadecimal number. And by giving this vector here, I can extract all of them in one go. Okay. And this can be assigned to, let us say, some b. So b will be that bit. So b1. Okay, so b1, b2, etc. you can expect. So what I can try and do is poly bits equals bit get. Take the polynomial which is given to you as a hexadecimal number and then go from n to 1. So start from 1 to n, but in the reverse sequence. So I gave a -1 as an increment because I want to go from n to 1, decrementing as I. Is that clear to everybody? Any doubts here? So poly bits will give me the ones and zeros, right? Extract the polynomial in zeros and one. I already have the current state in zeros and ones. So how do I get the next state? Okay, so first of all, it should return the next state. So first of all, what is the next state? So suppose I have 101. This is, let us say, my current state. There is a shift that you can do. Okay. If you do shift, it will return this the shifted state. So 1 has come here, 0 has come here, and unfortunately it also does a rotate. Okay, so it doesn't matter. So we can say next state equals shift. That's a right shift. Okay, current state 1 by 1 bit. So right rotate the current state and put in next state. Now we have done that. But what do I do? How do I get this bit? That bit, okay, I have to sample those bits which correspond to these ones and zeros. And I must take the XOR of all of them. Is that clear? So for example, in this example, I have to sample these two bits. So I will have 110000, and I'll have some state. Okay, I only have to extract the last these two bits. So how do I do that? Anybody knows? See, we can find the indices. Okay, see, suppose I have 110, right? If I say 1:3, right, and I do 110, what is a good way of extracting the indices? Hmm. How do I extract the last two bits? I mean the bits which are corresponding to 1. Uh, I want the first element and the second element. Hmm. I can write a for loop, not a big deal, but I don't want to write a for loop. I am trying to avoid writing a for loop. Right? Everybody understood the problem, no? I have this, the current state is, let us say, 110, and the polynomial is, let us say, uh, it is asking me to extract these two bits. So I want to extract the first bit and the second bit. Okay, maybe I can try this. That way. So what I can try to do is sample bits, sample positions is equal to. So I'll go from 1 to n, right? And within that I will write poly bits greater than 0. That means all the ones, whichever are ones, those are that it will extract, right? And then I can say this next previous state or the current state of sample position. Okay. So these are the ones which I am trying to sample, right? So I will have some values there, zeros and ones. Okay. How to take the XOR of them? See, how do I take the XOR of, let us say, 1, 1, 0? Okay. One simple way is you add everything. See, XOR is supposed to be sum, right? So that will give you sum. But I want the sum to be, you know, modulo 2. That means I can divide it by 2 and take the remainder. Okay. So I can say the next bit sum of I can take the sum of these, okay, and then I can take the remainder of these when I divide by 2, right? And that will be the next bit. And this must now become next state of 1 equals next bit. Okay. Hopefully I got this correct. Okay. So let us try applying it here. So suppose I take LFSR next state. Let us take a 3-bit LFSR. The current state is, let us say, 110. And the polynomial for the 3-bit LFSR is 110. So you can see that it has shifted this 1 and 1. And then it has XORed these 2 bits and put it here. Okay. So let us try instead of 110, let us try 0, 1, 0. So 0, 1 was right shifted here. And the XOR of 0 and 1 is not right, no? This should have been a 1. Getting the bits correctly. Let me remove these semicolons so that I know what is going on here. That is one way to debug this code. See the polybits is wrong. Polybits is wrong. Oh, I'm so sorry. This is not 110, right? It should be written as 0x something, right? I'm giving the wrong in. 0x6 is what I should have said. Sorry, sorry. So the polybits are correct, 110. Next state is 001. Then N2 out of bound 1. Polybits greater than. It's correct, no? Yeah, I think now it's correct. Okay. So, assuming that everything is correct now, so let us assume LFSR. So we'll start with 001. Okay. That gives me so one from 010 we go to 101. So if I had 101, I'll go to 110. If I go to 110, I'll go to 011. If I go from 001, I'll go to 101. Oh, this is correct. Yeah, 101. See, I think unfortunately I have given this 1 1, so it is sampling the last 2 bits. So I think this n:1 may not be the best way. So maybe I should have written 1:n because I am looking at the flip flops in this direction. Let's try this LFSR. So let us say we have a 3-bit LFSR. I started with 001. Now I think it's correct. Yeah, see, it's correct. See, I got the same states which I was getting here also, right? So 1, 4, 2, 5, 6, 7, 3. So I would have got the same states here. So if I go back, okay, let me do one thing. So I will say initial state. I'll add a small program here. Initial state equals. So first let me input n. So how do I start with the 0, 1 state? I will possibly have a 1 here, and I'll have zeros of 1 and n minus. Okay. So that will give me the initial state. Okay, I will have n minus 1 zeros followed by 1. Then I will say display initial state. Right? Or maybe while. Okay. Let us put a count here. While count is less than 2 to the power n, I will have to say display initial state. Okay. And then initial state becomes equal to LFSR next state using n and then initial state. And okay, so I'll have to remember all those for n equal to etc. I have to make a sort of a some sort of an array here. LFSR poly array for n equal to, we'll have to copy from Wikipedia 36C14. 36C14, maybe 3060. Okay. And B8 110. Okay. So let us assume that n equal to 2, 3, 4, 5, 6, 7, 8, 9. So beyond 9 I can't go. So if somebody gives me more than 9, I will stop. Okay. If n is greater than 9, then I will say sorry. Okay. And then maybe we should stop. Exit will exit. Okay. So let us execute this. Then n is red. So for this, let me just keep it simple 3. Okay. And then the rest I can execute as there. And I forgot to LFSR poly array. Okay. Oh, one more thing. This is n should have one. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'll have a dummy here for n equal to 1. Okay. So I'll send that, and then I will have to say current count is equal to count plus. So I'll have to do this. Mm, yeah. Yes. Mm. So it started with 0, 0, 1, then 1, 0, 0, then 0, 1, 0. Okay. Then no. Mm, did it give me all the states? Let me do it again. So 0, 0, 1, then 1, 0, 0. So these two bits have been shifted here, and the XOR of these two has come here. These two have shifted here, and the XOR of these two has come here. These two have shifted here, and the XOR of these two has come. Mm. It's wrong, no? So 1, 0, I should have got a 1 here. I think there is something. Mm, what is wrong? My function next state, it fails for 0, 1, 0. So let us do one more time. What is the problem? The problem is with the LFS next state. I think it is 0, 1, 0, is it? 0, 1, 0. So poly bits are 0, 1, 1 in this reverse order. That means these are the two bits that will be shifted. Next state is initially 0, 0, 1. See, how did that happen? I didn't say 0, 0, 1. I said 0, 1, 0, right? Oh, that is because it is shifted. Okay, fine, fine. 0, 1, 1. See, how did when I shift, okay, 0, okay, this is correct. 0, 1, and it shifted, that's correct. Then polybits is, uh, oh, it's correct here. 101 is correct. Then why is it not giving that here? I'm finding it very strange. Mm. Initial state is this display initial state. Initial state is the. Nobody knows what is going on. I think this function behaves perfectly fine. Let us start. Let us verify that this actually works. LFSR state 3, then 0, 0, 1, 0x6, then 1, 0, 0. This becomes the initial state. Then 0, 1, 0. It's correct. Then 1, 0, 1. It's working correctly, then why it's 1 second now. Ah, 1, 2, 3. 1, 2, 3. Why is this? So this is for n equal to 1. There is something wrong. Why the 0 does not come? I don't know what is very sad. It's a very strange bug. Okay, now it's okay, right? So 0, 0, 1, 0, 0 got shifted here, and then XOR of these two came here. 1, 0 got shifted here, XOR of these two came here. 1, 0, 1 got shifted here, XOR of 1 and 0 came here. 1, 0 got shifted here, 0 and 1 came here. Okay. So now let us be ambitious and try LFSR instead of n equal to let us try to give a slightly larger number. 9, let us try. Okay. So I'll try to be, okay, let us try one step at a time. 4, let us try. Oops. 4 at a time. Now from here I can execute everything in one go. So this should give me 15 states. Okay. They should all be unique. Okay. See, it's giving me 1, 8, nothing should be repeated. 1, 8, 4, 2, 9, then 12, 6, 11, 5, 10, and then 1, 1, 0, 1, 1. So nothing is repeated. Okay. So it is giving all the states. So we can try to be ambitious and verify whether it works correctly for n equal to 9 also. It will take some time. Okay. Now let us try this. See, it will give you all the 511 state to come. And they'll all be different states. Okay, you can verify later. This will, none of them will repeat. All these states will be different. Okay. Um, there may be some way to reverse this thing. Instead of I want 0x3, I want a hexadecimal representation of that bit vector. I will leave it as an exercise for you to figure it out. Um, Let us not waste time on that. But instead of writing all these ones and zeros, maybe it's easier to write the state. Okay, so let me give you this function and the program. Okay, this is a simulation of the LFS. So please copy it and try it. Any doubts? Any doubts? I'm sorry if I went very fast. Pooja, any doubts? Did you understand? Shalini, Vishnu. Anybody has any doubts? Pooja has said yes. Very good, Pooja. Anybody else has any doubts? So this was a little bit more, I would say, a little bit more advanced example where we showed that we can use MATLAB for even some digital simulation, etc. Okay, so let us take a maybe 5-minute break. Okay, like yesterday. Uh, Please refresh yourselves, right? Do some breathing, whatever, maybe some tea. Okay, then come back and we'll complete the rest afterwards. So take a 5-minute break. Anything else, guys, you want to ask before we go on? So, Akanksha, which college are you from? You can type in the chat box if you prefer. What about Laksha? Vivekananda. Oh, Akanksha is from Vivekananda. I think you may have mentioned, I'm sorry. Laksha, Nipunya, did I ask you? Nischal, Pooja, Anubhi. Nipunya is from NI. Okay. Nischal, Shalini, Vishnu. Vishnu, I think told yesterday, maybe or today. Central University. Yeah, I think she told. Shalini also told, I think. Let's see. Vishnu is from MIT Manipal. Good. So we have a number of different colleges being represented. Good. Okay, so in the remaining time, I thought I'll spend a little, about the various packages that are available. I had asked the people, the organizers to talk about the packages. See, Octave, you know, there is an Octave Forge. So you'll have to look at that. Right? This is a very nice, website. So you may know that MATLAB provides a lot of these packages or toolboxes. So the same thing is true here. They have provided a lot of packages, right? So all these various packages for communications, control. I have not installed all of them. I have installed a couple of them to illustrate. Okay. So let us start with maybe the symbolic package, which I installed. So you will have to say package install. Okay. I think I had given uh, the instructions are here. You don't have to even worry about it. Everything is clearly given here. Okay. So when you install it, if you have not installed, it takes a little time to do it, right? So first you have to, after installing, you have to say package load and whatever package you are trying to do, symbolic. Okay. So this loads that package, and now some of the functions which are there for symbolic are available. Right? So MATLAB is a numerical package, okay, but it can also do symbolic computation. Okay, so what does it mean? We can declare, let us say, P as a symbol. Okay. First time it will take some little bit of time. Afterwards, it will be faster. So sims t has declared t as a symbol now. It is not a variable. It's not that t will be 5 or 6 or some numerical value, but it is a symbol just like we recognize it. So now I can say y equal to sine of. So y is now a function of this t. And then if you want, I can say differentiate y with respect to t. So it differentiated sine t and said it is cos t. If you want, you can differentiate it one more time and it will come back and give you minus sine t. And if you want, you can differentiate it 3 times and it will give you minus cos. Okay. So you can take any complex function. For example, you can say y equals t square times sine of 2t. Okay. So this is a complex function. Okay. But you can differentiate it if you wish. So this is an example of symbolic computation, right? So t square multiplied by 2 cos at plus sine 2t multiplied by 2. In the same way, you can integrate it also. So you can integrate, let us take a simple function like z equals t times e power t. Then let us say integrate, let's say. So it is telling me that this is the integration of t per t. I think this is possibly the correct answer. You can also declare another symbol, let us say called okay, t is good enough. So let us say we can say sim sum. Let us say I want to sum t square. Sim sum sims, let us say n is another symbol. Let us say sim sum t from 1 to n. This means the sum of 1, 2, 3 up to n. Okay. So you may remember this formula, right? When I write 1, 2, so any function I can write here of t, and then this is the lower limit and this is upper limit. Similarly, let us say we wanted to go of t square. So this is the formula which we discussed today, early part. Okay. This is your n into 2n plus 1 into n into n plus 1 into 2n plus 1 divided by 6. It is just written in a slightly different. You can also see n cube, t cube. So it will try its best to figure it out, t power 4. This you may not have come across in your math books, right? But it is possible to add it. Suppose I want to add 1 plus half plus, okay, suppose I want to do 1 plus half plus 1/4 plus 1/8, etc. How do I do it? I can say sim sum 1 by 2 to the power t goes from 0 to infinity. I think infinity is written as for something. So you may know this is a very interesting series. 1 plus half plus 1/4, etc. is nothing but 2. Okay, so it is able to give you that. If you had stopped it at n, it will give you a formula, right? But if you stop at infinity, it will give you the answer as 2. Okay. So this is useful in a number of situations where maybe you're interested in getting a small formula or something like that. Okay. Sim, you can also do, the Laplace transform. If you want ut, you are supposed to say side t. Okay, this is your ut. Okay. So it is the same answer. That means from t equal to 0 only we want. Negative values we don't. Similarly, I can try sine 2t. Or maybe t times sine 2t. Okay. So it's pretty handy, right? You can even write exponential t. Okay. And you can also take the inverse Laplace by using the I Laplace. Okay. First, you have to declare sims S. Okay. Then I can say I Laplace. Let us say 1 over S square. Okay. Or 1 over S square plus 1. Okay. Or 1 over S square plus 4. Okay. So it is able to do fairly most of the stuff that you normally do in the class. It should be able to do. Okay. If nothing else, it can help you in, see, it may not give you the exact way, in your college, I don't think just giving the answer helps. I think there you are expected to show how it comes, right? But at least you can verify your answers or something, right? Um, there are many functions. So just like Laplace, and there is a, I think there is a sim substitute, I think is there, right? So suppose I have y equal to sine e to the power, let us say I declared a and b as symbols. Okay. I declare e to the exponential of minus a times t times sine of bt. Okay. So I have declared this as a function. Now I can say substitute in y a equal to 1. So I have substituted a equal to 10. Okay. Similarly, I can say substitute y b, let us say 2. Okay. You can take this and substitute in this function a equal to 1. Okay. So you can use substitute to simplify things by substituting some value. Okay. Then you can put t equal to maybe, let us say, uh, 0.1. Notice that it will leave it as a symbol, it won't evaluate. So if you want to force the evaluation, you have to say eval. Okay. So if you evaluate the final answer, you will get this. There is a function called easy plot, but it is not so reliable. Okay. So let us try plotting sine of 2t. Okay. This one works. Okay, it is able to plot sine 2t, etc. Let us plot e. So these kind of things it will do. Okay, again, it didn't do such a great job. It took minus 6 to 6, which may not be the best region. Okay. Um, okay. So it tries to calculate. See, the advantage of easy plot is you didn't have to specify what the range of t is. Okay. In the earlier plot command, we used to say t equal to some linear space or something like that, and then we will go ahead and calculate the value of the function at each of these points. I didn't have to do that. So they have tried to give an easy, slightly intelligent function, which can sort of guess which is the interesting part, but it doesn't always work. So it's not that intelligent sometimes. It may not do such a great job. But nevertheless, it is there. Okay, you can use it if you think at some stage you may want to plot some function. Okay. If you have a nice function, maybe this makes much more sense. Okay. So it's a exponentially decaying sinusoidal function. Okay. Slowly it will die down to zero. Maybe what really happens in real life is maybe it's a very slow decay, maybe 100 or something like that. So this is more likely in real practice. Okay, so it looks like this. So if you have a practical example like that, you may be able to Let us try a very simple example today of trying to use solution of differential equations. So let us try this example. Okay. So there is some V DC source and there is a switch here, and I may want to know what is the current that flows uh, in this RC circuit, or the voltage V here, something like that. Okay. So we know that the differential equation that governs this system is IR plus L 1 over C integral I. Okay. So if you differentiate this, you will get 0 equal to R di by dt plus I by C. So this is the differential equation. So we'll try to declare that here. So since R, C, IT. So I is a function of t, R and C are functions. So I will declare a differential equation called diff of I with respect to t uh, multiplied by R plus I divided by C. Okay. So this is my differential equation. And then you can say D solve. Okay. This differential equation. And you can specify the I forgot how to specify the initial condition. What is the initial current? The initial current, see when you turn on the switch, there is no charge on the capacitor. So there is no voltage across the capacitor. So the voltage across R is V. Therefore, the initial current will be V by R. Okay. So initial current is V by R. So we'll declare a symbol called V. And we'll have to say D solve. This is the differential equation. And I think this is the way to do. I0 equal to V by R. I think this is the way to do. I forgot. So it has come up with this equation. Okay, it is nothing but if you simplify it, okay, e to the power R log V by R, this R and R will get cancelled. E to the power log V by R is nothing but V by R. See, unfortunately, it has not simplified it sufficiently. Okay. It is the same equation that you are familiar with. It is that V by R times e to the power minus T by RC. Okay, I don't know whether it will allow you simplification. So let us write this. So this is my current. So simplify may work. See, simplify has done a better job. Simplify. Sometimes you need to do this. So this is an interesting thing. And how do you calculate the voltage across the capacitance? That is nothing but you know the voltage across capacitance VC equals V minus the current I multiplied by R. So that is this. You can also simplify this. Okay. So that turns to be like this. Similarly, you can go ahead and try an RLC circuit of some kind, right? Except that if you don't know the values of R, L, and C, it can be quite difficult. So it will solve it, but it will look very complicated, right? Are you following? Is everything okay? Guys? Yes. Had you seen this before? So if you know the values of R, L, and C, so suppose you take some, ready-made value of R, L, and C, right? Then it becomes easy. Suppose I say R equals 10 ohms, L equals 1 millihenry, and C is, let us say, zero point 0.1 microfarad. Now I can write a differential equation here. Let us say 10 volts, R, L, and C. Okay. So the equation is 10 equals R di by dt plus, I'm sorry, 10 equal to IR plus L di by dt plus 1 over C integral I. If we differentiate, we get 0 equals R d by dt plus L d square I by dt square. So it's a second order differential. So we can capture this R, L, and I. Then I can try to solve um, D equation. I think it didn't substitute, right? I0 should be equal to, see, the initial current is 0 because the capacitor acts as an open circuit. Okay. And we also need to specify I prime 0. It should be equal to, see, initially, you see there is no charge across the capacitor. Okay. And there is no current. So all the 10 volts will be across this. So V by L will be the initial value. So V by L, so 10 by L. So L is 1 millihenry. So this is the value. Hmm. It's not understanding. How did I? Oh, okay, okay. There is no. Okay, sorry. So see, it came up with the answer. Okay, so it happens to be an exponentially decaying sinusoidal wave. Okay, so this is something that you may have done in your first year electronics or something like that. Okay. It requires a lot of effort to do something like this. But if you have Octave, it sort of gives the answer right away. Was it interesting? Did you find it interesting? Okay. So this is an example of underdamping. Okay. So if I change R, L, and C, suppose R is very large. Suppose I take r equal to maybe 100. Okay. Then I say d equal to r times ti plus l times so this is a slightly higher value of r. So now if I try to do this out, okay, so this is also still sinusoidal. So let us try r equal to 1000. So now you can see that it is no more sinusoidal. It has become overdamped. Okay, so you will get two large exponential terms. Okay, and you can plot them using easy plot and try to see whether you can see the waveforms. Okay, so it is very easy to use this tool for solving differential equations, right? So that's another useful. Okay, so we have looked at symbolic, which gives you a lot of such things. Okay, I think there is also solve. Okay, so there are other related functionalities, but I thought this was very useful. So I went ahead and described it in a little bit more detail. Is this clear to everybody? Are you following? Akanksha is the only one who says I'm following. What about the others? What about the others? Nobody is following. Okay. All right. So there is one more package called control, which I have initialized. Okay. You will have to download it for yourself. This has a useful thing called transfer function. Okay. So if you say transfer function, the something like this. Okay. So it has understood this as 1 over s plus 1. So this is a transfer function that in control theory, if you have a some sort of box and it has a gain of 1 over s plus 1. So this is interpreted as 1 over s plus 1. Similarly, if this was 1, 2, 1, 2, 1, 1. Okay. So 2, 1 is 2s plus 1. 2, 1, 1 is 2s square plus s plus 1. So let us take an example. Maybe we'll do a very simple example. So what is the transfer function here? See, this is 1 over SC. Okay. So 1 over SC divided by R plus 1 over SC. So that is equal to 1 divided by 1 plus SCR. So it's a very straightforward example. I can make up more complex ones by trying to take maybe something like this. So this will be more complex. I will leave that as an exercise for you. So I will do the simple one, right? And then I will describe that transfer function here. So let us say R equals 10 ohms. C equals, let us say 1 microfarad. And we can say transfer from, let us say T equals transfer function. I have only one on top, and S is R times C and 1. The variable is this. So I have declared T as a transfer function. So I think there are many things available on transfer function, but one of the most important one is Bode plot. Okay. So if you do this, it should come back with the Bode plot of T. Okay. So which normally takes a lot of effort. Okay. What is the Bode plot? It shows the gain of that transfer function. Okay. As frequency is scaled from some value. Okay. In this case, they have intelligently chosen 10 to the power 3, and they have gone all the way up to 10 to the power 7. Okay. See, it has chosen this intelligently. It could have started from 10 to the power 0, but it chose 10 to the power 3 because the action is really happening here. So this is a very simple transfer function. It is a low pass filter. So all the low frequencies are passed, and the 3 dB frequency is somewhere here. Okay. You can see that it will show the values here. Okay. So if you point it here, it will show you that the frequency is 13K or 13.917K, and the gain is minus 0.039. So if you come down to minus 3 point something, so that will be the 3 dB frequency. Okay. So either you can do it manually like this, or you can try to automate it out. So, and this is the phase. Okay. When the frequency is very low, it is usually in phase. The capacitance practically acts as an open circuit, so the output and the input are in phase. But at very high frequencies, it is the capacitance that begins to take over, and the phase difference becomes minus 90. Okay. So you can calculate the Bode plot using this. If you want to know what else is possible, I suggest you go to this control. Okay. So if you have taken a course on control theory, and at that time you need any of these things, you can go here. See, you can see the repository here, details. So if you say function reference, it will show you all the functions. Okay, many of these are too advanced. Okay. See, this is what I use today. Okay, this is a transfer function. You can also use the state space model for the same thing, and you can use create a discrete time transfer function model in the DSP format. Okay, so these are more useful if you are going to take a course on control theory. Okay. Not everyone may be useful, but some of them may be useful. You can see the step response. So let us try to see the step response of RC. So if I give a step input to this function, okay, it will look like this. The time domain response is this. So initially it will be 0, and then slowly it goes to 1. So this is a step response. So let us take a slightly different transfer function. Earlier I had one more, right? This is fine. So let me call this R, and let us see what happens when I give a step. You can see that it will not be so stable. Initially, it sort of it has a lot of settling time. Okay. So that is the usefulness of step function. So ramp also, you can see how it for a unit ramp. Okay. Bode we already saw, right? Um, you may be able to see the poles and zeros. I don't know, it's available. Stability also, I think it is there. I don't recall where it is, but it is there. There is one function which tells you, you can see the impulse response. Uh, um, Nyquist may be useful. So this gives you the Nyquist diagram, which sometimes they ask you to do in the college. Okay. So these are very useful if you are trying to, because both these, let me much better. Yeah, so this is a Nyquist diagram. Okay. Um, in the same way, there are a few other ones like signal. Okay, so there is a signal package. If you have taken a course on signal processing, so there you may be interested in all these signal processing, maybe Z transforms and RMS value of the signal, convolution. Okay, F50 is anyway supported at as part of the main itself. It's supported, so you don't need this package to calculate F50. So F50 can be found out directly, right? So you can try that exercise, right? Suppose I take a signal and calculate the okay, let us take a signal. Maybe I have not told you about random numbers. So there is a function called rand. Okay. So this gives you a 10 by 10 matrix of random numbers. Okay, all in the range 0 to 10. So if I say 1 to 10, I have got 10 random numbers. Okay. So these are uniformly generated random numbers. Uniform in the range 0 to 1. If you want, let us say, an exponentially distributed random number, so you can say expo x prime. Instead of rand, it will be x prime. It will take as input the lambda value or mu value, whatever you call it. Let us say 10. And again, maybe I want to do 10. So here the mu value is 10. So similarly, you can binomially distribute a random number. Bino-rand. Here you need n and maybe 5, and I can have. So n is the n and p values have to be given, and the number of random numbers you want to generate. Okay. So this is to be interpreted as I toss a coin, fair coin, 10 times, and I want to know how many heads are coming. Okay. In one experiment, I got 3 heads, 7 heads, 2 heads. So they have supported binomially distributed random numbers, exponential, many such are supported. Okay, you can take a look. Okay, so these are useful if you are doing a course on any statistical signal processing or anything of that nature, right? Uh, these will be very handy to you. Okay? So let us assume that there is some voltage. Okay, let us assume that the frequency is sine of. There is one sinusoidal. Let us say 10 times sine of 2 pi. Let us say 50 hertz and linear space 0 to 2 times this is my one sinusoidal signal. To that, I am going to add another sinusoidal signal. Let us say it is sine 6x. Okay, 6 pi, maybe 50. So, mhm. Somehow. 1 minute. Okay. So this is an ordinary sinusoidal waveform. Now to this I'm going to add maybe sine 6 by 50 t. Now let us say plot t. So this is a slightly distorted sinusoidal waveform, okay, because I added some. Let me add now some random data. Okay, so let us say I have added how many points are there in V length of T is this is the number of points, 100 points. So I'll have to take some, let us say, rand. So this will be some random values. I'm going to add this to V. So it will have all kinds of random noise, etc. Okay. So I have a bad sinusoidal. It has a 50 hertz component, which is a main component, plus there is a harmonic, which is a third harmonic, plus there is some noise also. Okay. So maybe I'm interested in knowing if I get this kind of a sinusoidal signal, a noisy one, maybe we want to know which harmonics are present, right? So for that, you'll have to take the fast Fourier transform of this function. And then, see, you want the power spectrum. So FF will have, unfortunately, all complex numbers. Okay. So you will have to first calculate the absolute value. The absolute value of FF will give you these kind of things. Then AFF, if I square each term and then finally divide it by 100, the number of times, number of terms, this will give you the power spectral density. Now, if I try to plot the power spectral density, okay, how many so if I plot you can see that it shows me that there are two significant components. One at this main component, okay, and then there is another which is a lower one. So this is the third harmonic it has detected, and there is also some random noise. So like this, you can also go and try to do fast Fourier transform and things like that. Okay? So there are many such packages. You'll have to take advantage of these for your projects and things like that. Okay? So I will let you explore them further, right? So let us start summing up what we have done so far, right? So I have engaged you on two different dates. So we spent almost 5 hours, right? A little bit more than that maybe. And our main concentration has been to understand how to use Octave, which is a substitute for MATLAB, uh, which is a free substitute. But as you know, anything that is free has some difficulties. First of all, it can be slow. compared to MATLAB. Secondly, sometimes if it doesn't work, okay, they are not going to give you any guarantee. Right? If something doesn't do its job, or you find that there is a bug or something like that, then it is an open source software, so you can at most report it to the people who developed it, right? And hope that they will fix it, right? So they keep introducing improvements and keep releasing new versions, right? So in the new versions, these problems are hopefully sorted out. And today it is already at version 6 or something like that. So most functions may have been stabilized. Okay. So bugs will slowly possibly go away, right? But if there are some bugs, okay, you can't really, force them to fix it for you or something like that, because it is open source, public domain. So you can at most bring it to their attention by filing some sort of a complaint or whatever. But like that, there are so many users, they may all be asking questions. Some of them may already be solved. Right? So you will have to follow the forums, okay, in order to get answers to your questions. Okay? MATLAB, on the other hand, because it's a paid software, if you have paid, then hopefully, even there, they may not individually come and help you, right? But at least there may be some forum which is more, um, they are entitled to a response. If you ask a question, they can, at least somebody will respond and point you to some help, something. They may not handhold you, but they will say, hey, why don't you read this, or why don't you look at this documentation? So we looked at a number of things. The basic commands, we looked at vector creation, matrix creation, some linear algebra operations, how you can write for loops, functions, while loops, right? If then else, etc., etc. Then we looked at how you can use the Octave to maybe solve differential equations, right? Transfer functions. You can even do, yesterday I think we looked at, how you can do electrical engineering kind of problems where maybe you want to know where is resonant frequency, you want to plot the impedance as the frequency is varied. Uh, we looked at various kind of plot functions, subplots, right? So there is, you know, a lot of variation, a lot of commands, and it requires exploring, right? Even I can't claim that I have looked at all the commands. Okay, so I may sometimes figure out something that I didn't know. Okay? So if you don't know that there is a command, unfortunately, we end up writing a lot of code ourselves. So try to see, the documentation and avoid having to write. See, for example, if you didn't know that this bit get was there, right, then you will unfortunately write your own code for bitget, which is not required. Right? So I also didn't know about bitget. Only when I was preparing for this class, I figured out that there is a bitget. Okay? So like that. So that is more or less what I had in mind. I think we are at the end of the time anyway. We have a few more minutes. So I will spend the remaining minutes, asking you questions, or you can ask me questions. So it looks like only about 7 people have survived, right? Yesterday we had 18, today we are down to 7, right? At least those of you who survived, hopefully you got some value out of this class. So give me some feedback. Put your chat, tell me what you learned and how was it, how are you planning to use it? You can put it in chat if you want. Anybody wants to say anything about what you learned? How are you planning to use? Nobody has any thoughts.
Hello, sir. It was a great session indeed, and we had a lot of things to learn. And maybe the participants also could learn so many things which they would be using further in their studies and in their further detailings and stuff. So,
Yeah, good,
so
good. I'm curious to know where you will apply it. I mean, you may now be in second year, third year, fourth year. I don't know which year you are in. So curious to know which functions were most useful to you and where you are likely to use. Which one did you find most useful?
yes, sir. So we'll be working upon control systems now, and so
Okay,
there
if you are
that
taking
is
a course
where we.
in control systems, please see many books use MATLAB as a tool. For example, if you see books by Ogata, etc., they have MATLAB code. Okay, so now that you know how to use it, you can use Octave and try to bring up those exercises, etc. you know Almost all books on signal processing, they are based on MATLAB. Control theory, they use MATLAB. So MATLAB is very popular, and Octave is a substitute for MATLAB. So you can use and projects, of course, right? So sometimes even let us say you are doing a course on some other mechanical engineering or something like that, right? And there may be a lot of competitions there. How to calculate the maybe center of gravity or something like that, right? It'll be nice if you can write a Octave program to do those things, right? And for all plots, etc. I recommend you start using MATLAB for most of these day-to-day routine things.
Yes,
Anything
sir.
else?
Absolutely.
Anything
So
else before we break?
So I guess we don't really have questions from participants. So I would like to hand over the session to Rubini now. Do we have you here, Rubini?
Yeah, Rashi. Yeah, yeah, yeah. Thank you very much, sir. It was a great session. I hope participants loved the session and learned a lots of uh, things about the Octave and the software. And I hope it will be really benefit for them to make their projects in college. And yeah, I hope participants learned a lot
Yeah,
from the
I
class.
also hope so because not many people survived the second day. So, how many
Yes.
people were there registered in this class?
So going by the registration, we had around 139 registrations.
Oh my God. So, I
Yes.
don't think at any point we had more than maybe 18, 20 were the maximum.
Yes,
So, I
sir.
think
That's
you
right.
need to do something about it. Give this feedback, right, to the
Sure.
organizing committee and say that, see, what is the point in 130 registrations and only 18 in the first day and finally 7 or 6 in the last day? So I think it's, see, we don't know what was required also. See, when somebody says, I want Octave, so I can only guess what is being requested, right?
Yes,
So
yes.
anyway, at least I hope that some of you, even if one of you uses it in some meaningful way for your college projects, etc., I will consider it to be, my pleasure for having interacted with you. Okay, thank you.
Yes, sir.
All right,
Thank you,
bye bye.
sir.
All the best to
Bye.
all of
So,
you. Stay.
uh, yes, sir. So also we have a small token of appreciation for you. So
Oh,
yeah,
okay,
we'd
no
like to give
problem.
that.
Yeah, yeah. Anyway, thanks a lot, uh, everybody. All the best to you. Huh?
So thank you so much, sir, for joining us
Okay,
for
okay.
this.
This is sure, sure. No problem. Okay. Thank you so much.